To set the debt-to-service ratio, the plant cost must first be determined. Below is the estimated cost for a similar plant done by the Idaho National Lab. For the analysis purposes, the overnight cost of $2 billion is used as financial costs are calculated separately. Next, I cross-indexed this estimate with the MIT 2025 study on modular reactor top-level estimates, which showed similar values. The MIT study also included expected learning curve results. Given the first-of-its-kind cost of $4 billion, the Unit 10 cost of $2 billion is within expected values. This effort is assumed to be taking place as part of California decarbonization plan based on the expectation that Natrium systems are used instead of in conjunction with offshore wind based of the California plan decarbonization scheme. Given a $2 billion reactor cost and a 75/25 debt-to-equity ratio, $1.5 billion will require financing. However, the investment tax credit, ITC, for a reactor of this type will range from 30 to 50%. For the sake of simplicity, it is assumed that the full amount of the credit will be applied to reduce principal at an ITC value of 40% to account for ITC issues and fees preventing 50% value. The values used for revenue and operating expenses were previously developed. An 8% discount rate is used with the assumption of significant government support for financing. The model was then run for 3 different scenarios. S1 electricity rate used at $90, and all other variables held constant. This is based on the projected value required for floating offshore wind. S2 rate used at $60. The is based on proposals by natural gas companies to include sequestration costs and keep gas plants. S3 rate used at $60 but capital costs increasing to $3 billion due to 50% underestimation in prior studies. Other ratios remained constant. Note: for all scenarios, depreciation was simplified in model to offset income for a given year until used up. In real life, due to accelerated depreciation, it will exceed income. Modeling carryover is a complication that does not change the underlying value proposition. The results for average debt-to-service ratio are as follows. S1, 3.83, which is far above required due to ITC. S2, 2.15, which is still strong. S3, 1.44, which is above lending requirements of 1.3. To drop below 1.3, capital costs need to be to rise 115% to $3.3 billion. Other factors such as interest rates can achieve the same type of impact. The levelized cost of electricity will use the following inputs based on the same factors discussed in the debt-to-service ratio. The scenarios here are 1. $2 billions with no ITC. This allows for unsubsidized comparisons with other energy sources and locations. It also provides a reasonableness check for the model as a whole. 2. ITC included. 3. $3.3 billion with ITC to provide figure for cost at max DTCR. 4. $3.3 billion with no ITC. Results are as follows: $per MWH. S1, 77.8. S2, 51.7. S3, 66.3. S4, 110.4. The values shown here are consistent with model results. Since the Natrium system includes a thermal storage system, as mentioned above, model values are slightly higher than actual operations are likely to see. This is consistent with the calculator found on the TerraPower website that unfortunately does not show the numbers behind its calculation. The internal rate of return, IRR, is calculated within the model using the data developed previously as discussed in both the DTSR and LCOE results. As in the case of DTSR, the model was then run for 3 different scenarios. S1 electricity rate at $90. S2 rate used at $60. S3 rate used at $60 but capital costs increasing to $3 billion. Other ratios remain constant. The results are as follows. S1 IRR equals 35%. S2 IRR equals 23%. S3 IRR equals 19%. These IRR values all represent returns sufficient to proceed with the project. A cursory examination would indicate the DTSR values are likely to be the limiting factor rather than IRR on decisions at the company level to proceed. Given the high capital cost, length of operation, and interest rate sensitivity along with government support expectations, these are general conclusions with may change. It is worth noting that the Natrium system was designed to complement renewables and not replace them. Its ability to use thermal storage is a key element that separates it from other direct competitors and provides that synergy. Given the history of nuclear plants, it is worth touching on items that might cause this IRR to be overly optimistic along with those working in its favor. 1. Schedule delays. The model does not account for a significant delay between project construction and the start of revenue generation. By way of example, a 3-year delay, not uncommon in nuclear, can drop a 1.44 IRR to 1.1. In fact, the model already understates this impact by not modeling pre-startup payment requirements. 2. A significant portion, 50%, of this project is non-nuclear and should therefore be more predictable. In addition, while the use of sodium as a coolant adds fire risk, this is projected to be more than offset by the ability to operate atmospheric conditions, making it both safer, does not require pumps for shutdown, and eliminates containment requirements. 3. As discussed previously in the risk discussion, the plant is dependent on an enhanced version of uranium reactor fuel. Should domestic sources for this capability be delayed, it could entail impact on the IRR results significantly. Summary. The Natrium system meets the requirements for a capability to complement other renewable sources in California.